All right, hello everyone. This is Dr. Gallenstein, and I am back again for lecture number 5. In today's lecture, what we're going to do is we're going to go into a little bit more detail into how we calculate our estimated parameter values, our estimated coefficient values. So how do we calculate beta 1 hat? How do we do it? And then we're going to talk about some of the assumptions that we need to make for us to say that that's a good estimate of the true beta 1. What assumptions do we need to make so that we can claim that our estimated coefficient values are good estimates of the true coefficient values? Okay, and then we're going to talk about a violation of one of those assumptions, probably the most important one, when we talk about what's called omitted variable bias. And then, in typical fashion, we will take what we are lecturing on and what we're talking about, and then we're going to demo it all using Stata. All right, so with that overview, let's get started. The first section here is called ordinary least squares. Ordinary least squares is the methodology that is most commonly used to estimate coefficient values. All right, so this is the how. This is the how we do it, okay? And I want to talk about what it is and kind of give ourselves some intuition as to how this calculation works. We won't go into all the details, but we're going to give an overview and give the intuition. All right, so to begin with, let's take a look at a generic, simple regression model. We have a dependent variable y with observations for each individual I. And then we have an independent variable x with observations for each individual I. We have an error term for each individual I. And then we have the population coefficients. So we've got beta 0 and beta 1. All right, so what we're saying here's our population regression model. We're saying that the dependent variable is a function of the independent variable x. And this linear regression model accounts for or describes the dependent variable. Okay, so we have this is our population regression model. And what we're going to do, we never know the true population regression model because we never have all the data. And so what we're going to do is we're going to estimate this, right? And what that means is that we're going to find estimated values of beta 0 and beta 1. All right, so we'll estimate beta 1, and that estimate of beta 1 is going to be the value that we are most interested in because we want to know how x and y are related. We want to know how much does y go up or down with a 1 unit change in x. All right, so we want to know what this beta 1 is. We want to know what the population beta 1 is. So because we can't calculate it directly, what we're going to do is estimate it by finding beta 1 hat. All right. So the question is, how do we find beta 1 hat? How do we calculate it? Where does it come from? All right. Well, to do that, let's lay some foundation. All right. To calculate beta 1 hat, what we do is we use a method called ordinary least squares. That's just the name of the method. Okay. And I'm going to show you kind of what that looks like. But first, actually, let's just kind of define it. So what we do is we calculate the coefficients by minimizing the sum of squared residuals. All right, so let's define a residual. So the residual is the difference between an estimated predicted value of y and the observed value of y. So it's kind of like an empirical error term. So this is kind of what it looks like down here. So I'm saying r, I'm using the letter r here to represent the residual. All right, so each individual person has a residual. All right, and the residual is the difference between that individual's particular dependent variable value, their particular value for the dependent variable, minus that individual's predicted dependent variable value that would come from a regression model. That will come from an estimation of the regression model. All right, so that's where this y I hat comes from. All right, the difference between them is the residual. All right, the difference here is the residual. Okay, so what we're going to do is we're going to use this residual to find beta 0 hat and beta 1 hat. Now, before I go on and go into that in a little bit more detail, let's just kind of have some intuition here that might predict where we're going with this. So what we want is we want values of beta 0 hat and beta 1 hat that give us a good regression line, a good regression model that fits the data. Remember, I was saying, a good model is going to fit the data well. It's going to describe the data well. Right? And so just using that intuition, we can think, okay, I'm going to want a model that has small residuals. I want models that has the smallest possible residuals possible. The lowest residuals. I want the least residuals, right? Because that would mean that that my model, my predicted values that come from my model are very close to the true values, or to the observed values. Okay, so we could just use our intuition. We can say, you know what, a good model that fits the data well would be a model that has small residuals. All right. And that's kind of the intuition, is that we are going to calculate beta 0 hat and beta 1 hat by finding the value of beta 0 and beta 1 that gives us the smallest residuals. All right, so there's our intuition. Well, let's make this even more clear. All right. So first, let's be more clear about what this yi hat is. So yi hat is the linear is equal to the linear function of the independent variable x from the estimated model. All right. And so yi hat equals beta 0 hat plus beta 1 hat times x. All right, that's what yi hat is. It's beta 0 hat plus beta 1 hat times x. All right, this is what yi hat is. Even if we haven't estimated the regression model yet, there will, if we estimate the model, there will be some y 0 hat and some beta. Beta 0 hat and some beta 1 hat. Okay, and so we know that this is the yi hat. Now, just to kind of show the calculation, let's plug this expression into our expression for the residual. I remember it's yi minus yi hat. We're going to plug this in for yi hat. Okay, and so now we have a function. We have the residuals as a function of beta 0 hat and beta 1 hat. All right. And so what we're going to do, what we want to do, is we're going to sum the squared residuals. We're going to take the residuals, right? So this is r, and we're going to square them, and we're going to sum them up. So each individual person has a residual. We will square that residual, and then add it up for all the individuals in the data set. That will give us the sum of squared residuals. That will give us one. That gives us one expression that kind of captures how far away a fitted value of the regression is from the observed data values. All right, and then what we do is we find the values of beta 0 hat and beta 1 hat that minimize the sum of squared residuals. Whatever value of beta 0 hat and beta 1 hat that minimize the sum of squared residuals, those are going to be the beta 0 hat and beta 1 hat values that we will use. And so again, the intuition, what we're doing here by creating this sum of squared residuals is we're getting kind of a measurement of how big the residuals are. In sum, all of them, all the residuals together. How big are the residuals? And then we want to find the beta 0 and beta 1 values that would give us the smallest residuals. All right? And those will be the best estimates of beta 0 and beta 1 that we can find. All right. So let's kind of reinforce our intuition here by looking at a graph. All right. So here's kind of a simple graph, and I've got 5 data points on it. All right. We've got the independent variable on the x-axis, dependent variable on the y-axis, and we've got 5 data points. And what we do with a regression is we fit a model, a linear model, a linear line. We fit a linear line to the data. Right? We fit a linear line to the data, and that line will be a function of beta 0 hat and beta 1 hat. So let's say that this is our fitted line. This is our regression line. This is a function of beta 0 hat and beta 1 hat. In fact, we can say this line here is equal to this. Here's this line. Y hat equals beta 0 hat plus beta 1 hat times x. That's what this line is. All right. And the difference between a particular value on this line and the observed value is the residual. All right, so the difference, we're saying that this is person 5. The difference between person 5's observed dependent variable and then their predicted dependent variable is called the residual. All right, so there's residuals for all these different individuals. So this is person 3 and person 4 and person 5. Okay, so this is the fitted regression line, and the regression line will be a function of beta 0 hat and beta 1 hat. By choosing beta 0 hat and beta 1 hat, we choose what this line is. So I've drawn this line here, but we could have different lines. The line is determined by what the beta 0 hat and the beta 1 hat are. All right, so we will choose the value of beta 1 hat and beta 0 hat such that this line is the best fitting line, the line that fits the data the best, and that would be the one that has the smallest total amount of residuals. All right, so we find the values of beta 0 hat, beta 1 hat that minimize the sum of squared residuals. This is a way of kind of minimizing the residuals. Whatever the beta 0 hat, the beta 1 hat, whatever values of those that would give us the smallest amount of total residuals, in the data, whatever would do that, that will be, whatever values, those will be our estimate values for beta 0 and beta 1. All right, so by choosing beta 0 hat and beta 1 hat in this way, we find the regression line that best fits the data. Therefore, it will be the best estimate of the true population regression line, the smallest residuals. Well, you might ask, kind of as an aside, well, why square it? We square it because we want to get rid of the negative values. You'll notice that this residual is going to be negative. This residual is going to be negative. We can't just sum up all of the residuals. If we summed up all the residuals, some of it is going to cancel out. We don't want that. What we want is a measurement of the total amount of residual, the total amount of variation from the fitted line. And so that would be the sum of the squared residuals. Okay, and then I want to clarify one thing. So I hope this intuition is making this clear what we're doing. I want to clarify one more thing here. So this slide, this comes straight from regression number. Lecture 3 on Introduction to Regression Analysis. You remember, we've got some true linear model, some true population line, a regression function that is the true linear relationship between the dependent variable and the independent variable. And then we're going to have some estimated line, which may or may not be a good estimate of the true line. I want to make a distinction here between the residual and the error, just to make sure that that's clear. The residual is the difference between the estimated linear model and the observed data value, whereas the error is the difference between the true population regression model and the observed data value. Okay, so this is the residual, this is the error. And we think what we're going to do is we're going to create an estimated linear model that will minimize our residuals, and that will be the best estimate of the true model that we can generate. All right, so then how do we do it? What's the math look like? Well, we're not actually going to go through the derivation of this. We're not actually going to solve it out. But what we're going to do instead, I'm just going to show you what kind of the equations are. So if we actually performed this process, we did this minimization, and then we calculated the beta 0 hat and the beta 1 hat that give us the smallest residuals, what we would find would be these values here. Beta 1 hat is equal to this expression. What it is, it's the sum of, for all the individuals in the data set, the sum for all the individuals in the data set of the difference between the individual x value and the mean times the individual y value and the mean, divided by the sum for all the individuals in the data set of the difference between the x value and the mean squared. All right, this is our beta 1 hat. And then to find beta 0 hat, we plug that into this expression here, where we take the mean of y minus beta 1 hat times the mean of x. Where x is the where xi is the observed value or an observation of x for individual I, and x bar is the mean. Same thing for y. And then this is the sum expression. So it sums the values from I equals 1 to I equals n. Okay, so then this is kind of the math. This is the guts. This is how it works. This is how we actually calculate the estimated values for beta 1 and beta 0. To give us a little bit more intuition, give us some insights into what beta 1 hat is mathematically, we can also express beta 1 hat as this expression here. So it means what we already showed here is equal to this. What is this? This rho xy hat, this is the sample correlation coefficient between x and y, times the standard deviation of y, the dependent variable, divided by the standard deviation of x, the independent variable. So this expression here actually equals the correlation times the standard deviation of y divided by the standard deviation of x. All estimated values, so they all have hats. And that gives us a little bit of intuition. So in short, beta 1 has basically an adjusted correlation between the dependent and independent variables. It measures how the two variables are correlated with each other. A significant beta 1 hat indicates that there is a statistically significant degree of correlation between x and y. All right, so that gives us an idea of what this beta 1 hat is, how we calculate it, and what it means. We're actually going to do this in the demo. Okay. Now, so if that's how we calculate it, or at least that's the most common way of calculating our beta 1, our estimate, our beta 1 hat, that this method is going to rely on some assumptions. And if these assumptions hold, then we will find that beta 1 hat is the best possible estimate of beta 1 that we can get. Beta 1 hat will be the best possible estimate of beta 1 that we can get. All right, if these assumptions hold. And what we're going to do over the next couple of lectures, so this one and then the 2 lectures after that, is we're going to go through these assumptions. We're going to talk about what they mean. We're going to talk about what happens if they're violated. We're going to talk about how to solve, we're going to talk about what problems arise when they're violated. And then we're going to talk about how do we solve those problems when they do arise. Okay, so that's going to be the objective. That's what we're going to be working on over the next 3 lectures. All right, so I'm going to go over the assumptions now, and then we're going to go into detail on the first assumption. And then next lecture we'll go into detail on another one, and then the next lecture another one. All right. All right, so these are the assumptions for OLS. The first one, and I'm just going to go through these. They're not all going to be perfectly clear today because I'm going to go into more detail on them later. All right, so the first one is the conditional mean independence. So what this is that the expected value of the error term conditional on the independent variable is equal to 0. All right, we'll come back to that. We're going to talk about this a lot more today. The next one is constant variance. That means the homoscedasticity. All right, we'll talk more about that in 2 lectures. There's the variance of the error term conditional on x is constant. So the variance, the variation in the error term doesn't change given a change in x. All right. Third is that no independent variable is a perfect linear function of another variable. So there's no perfect multi-collinearity. We've got a lot of big words here. We'll go more into that next lecture. Assumption 4 is the observations of the error term are uncorrelated with each other. Assumption 5, the error term has a zero population mean. And 6, the error term is normally distributed. All right, so we'll take these in more detail as we go. If all these assumptions hold, so if these assumptions hold, then beta 1 hat is blue. All right, and blue is an acronym that stands for Best Linear Unbiased Estimator. Basically what that means is that beta 1 hat is the best possible estimate of the true beta 1 that we can have. All right, best means that it's the most precise. It's the most precise estimate. I'll talk more about that in the next lecture. It's linear. Linear means that it is a parameter from a linear model. All right, we've already shown that the regression models that we're using are linear. Okay. It's unbiased. Unbiased means that there is no bias in the estimate of beta 1. I'm going to talk about bias today. Bias is a very important issue. All right, so this beta 1 hat, if all the assumptions hold, beta 1 hat is unbiased. All right, that is essential. We'll talk about that today. An estimator means it is an estimate of the true population beta 1. So if all the assumptions hold, then the beta 1 hat that we find using the OLS method, the ordinary least squares, so I'll use the term OLS, that means ordinary least squares, is the best possible estimate of beta 1 that we can have. And so then it becomes quite important for us to be able to say that our assumptions hold. It becomes important for us to make sure that our assumptions hold. So we're going to spend the next 3 lectures talking about that. All right. The first one. All right. So that gives, all right. These 2 slides here, what we're just done, we've given an overview. All right. We're going to talk, we've got some assumptions. If these assumptions hold, then beta 1 has the best possible estimate of beta 1 that we can have. All right. So then it's it's important that these assumptions do hold. And we're going to spend the next 3 lectures talking about the assumptions that are most likely not to hold and the implications if they don't hold. What are the implications and what problems does it create and how do we solve them? Today we're going to focus on the conditional mean independence assumption. All right. So today we're going to talk about this one. What problem does that cause? What does this mean in practice tangibly when we're actually doing an econometric analysis? What does this mean for us tangibly? How do we know if we have a problem? What's the problem, and how do we solve it? All right, that's what we're going to do today, in the rest of the lecture, and then in the demo. All right, so then let's take it. So this is going to be called omitted variable bias. All right, and we're going to make that real clear. All right, so talking about that first assumption, the conditional mean independence. All right, so what we're saying here. What we're saying effectively, what this expression means, is that there is no correlation between the error term and the independent variable. All right, so there's no correlation between the error term and the independent variable. All right, that's what this first assumption means. The independent variable is not correlated with the error term. All right, now why would it be correlated with the error term? Let's make sense of that. So remember, the error term accounts for all the variables that are excluded from the model. The error term accounts for all the variables that are not included in our regression model. Okay, so x will be correlated, so our independent variable will be correlated with the error term if there is some other variable, let's call this other variable z, that is excluded from the model but is correlated with x. Now, does that make sense? The error term accounts for all variables that are excluded from the model. And so if there is some other variable, let's call it z, if there's some other variable z that is excluded from the model but is correlated with x, then x will be correlated with the error term because the error term is accounting for this other variable that's missing, and x is correlated with that other variable. Okay, so this assumption is saying that the error term is not correlated with x. The independent variable is not correlated with the error term. This assumption will not hold if there is some variable that is excluded from the model but is correlated with x. Okay, so here's the conditions. If there's correlation between x and z is excluded from the model, so if there's correlation, it means it doesn't equal 0. All right, so if there's correlation between x and z is absent from the model, then this assumption will not hold. This assumption will not hold. All right. Now what happens if it doesn't hold? So the conditional mean independence assumption will be violated if x is correlated with the error term. And this will be true if there's a variable z that is excluded from the model but is correlated with x, right? All right. So it will be violated if that's true. Now if z is also correlated with y, that means z, this omitted variable, this variable that is excluded from the model, if that is also correlated with the dependent variable, all right, the correlation coefficient is not equal to 0, then beta 1 hat will be a biased estimate of beta 1. All right. So this is the consequence of violating the conditional mean independence assumption. If we violate this assumption, then what's happening is that beta 1 hat will be biased. Beta 1 hat will be biased. As long as this omitted variable, we're going to call z an omitted variable. A variable that is excluded from the model is omitted from the model. So z is an omitted variable. So if the conditional mean independence assumption does not hold, which is to say that the omitted variable is correlated with the independent variable, and the omitted variable is also correlated with the dependent variable, then beta 1 hat will be a biased estimate of beta 1. All right, so if z is excluded from the model and these two conditions hold, then beta 1 hat will be a biased estimate of beta 1. All right, let's give an example of what this would look like. And then let's talk about what does bias mean and the implications. So let's take our standard example. We've got income is a function of education. All right. And let's ask ourselves the question, will we have a biased estimate of beta 1? So if this is our model, will we have a biased estimate of beta 1? So if we're asking ourselves that question, what we need to do is we need to think. So can we think of another variable that would explain income, be correlated with income, and would be correlated with education? Because all the other variables, so in this simple model, every other variable is in the error term. All variables other than education is in that error term. All right, so can we think of another variable that would explain income and would be correlated with education? So here's an example. Age. Age is not in the model, so it is accounted for in the error term. And so age will be a good example of something that could cause bias. Older workers probably make higher incomes because they have been employed longer. So that would mean that age is probably going to be correlated with income. Older workers also are probably to have higher levels of education. They just, they've had more time to accumulate more years of education. And so, just based on our intuition here, we can say that, yeah, the correlation between education and age is not going to be 0. And the correlation between income and age is not going to be 0, which would mean that the beta 1 hat, the estimate of this beta 1, will be a biased estimate of the true beta 1. All right, so we will have bias if these two conditions hold. So if we can think of a variable that excluded from the model, but correlated with the variable in the model and correlated with the dependent variable, then this implies that we will have a biased estimate of beta 1. Okay, well that sounds bad, but what is bias? All right, so if the conditional mean independence assumption does not hold and the excluded variable is correlated with the dependent variable, then beta 1 will be bias. What is bias? Well, to make this clear, let's just remind ourselves that beta 1 hat is a random variable. It's kind of like the it's kind of like the sample mean. If we go back to, remember the sample mean, every time you collect a data set, you'll find a new sample mean. And that sample mean itself is a random variable, and it has a distribution, the sampling distribution of the sample mean. And that sampling distribution of the sample mean is going to be a normal distribution, and it's going to be centered at the true population mean. So if you remember that, beta 1 hat is very much like that sample mean. Every time we estimate our regression model with a different sample population, we will get a different value for beta 1 hat. This implies that there is a distribution for beta 1 hat, and this distribution has a mean and a variance, which we'll talk about later or in another lecture. All right, so let's just imagine, here we go. We have a distribution of beta 1 hats. All right, so beta 1 hats follows some distribution. And when you run your regression model with a particular sample, you will get a beta 1 hat from the distribution of possible beta 1 hats. You could have one that is right at the mean, or you could have one way out here or way out here, but these ones are a lot less likely. You're much more likely to get a value of beta hat that's somewhere around the mean. All right, so your particular beta 1 hat value is a value pulled from the distribution of possible beta 1 hat values. All right. Now, what does it mean for your beta 1 hat estimate to be biased? All right. Well, if the mean of the beta 1 hat equals the true beta 1 hat, then the estimate is unbiased. Just a little typo here. Then the estimate is unbiased. Is unbiased. All right. If the mean of beta 1 hat equals the true beta 1 hat, then the estimate is unbiased. All right. So if you remember with our sample means, every time we collect a data set, we have a sample mean. That sample mean is a random variable. There is a sampling distribution of that sample mean. And the mean of the sampling distribution of the mean is the true population mean. Lots of means. I'm sorry. Okay. If the distribution of beta 1 hat, all right, it's a random variable, if the distribution has the mean as the population mean, then it's unbiased. That's what that would, that's the, excuse me for repeating, that's the meaning of beta 1 hat being unbiased. All right. Beta 1 hat is unbiased if the average, let's use average, if the average value of beta 1 hat is equal to the true beta 1. And what does that imply? If your beta 1 hat is unbiased, that means the most likely values of your beta 1 hat are going to be around the true beta 1. That's what it would mean to be unbiased. We like things being unbiased because it means that it's much more likely for us to observe a particular beta 1 hat value that's close to the true value. All right. You can see here that if the mean, the average of this beta 1 hat distribution is equal to the true beta 1, then it's very likely, it's much, much more likely for you to observe a beta 1 hat value that's close to the true value. And it's very unlikely to observe a beta 1 hat value that's really far away from the true population value. All right, so that's why unbiasedness is so important. See, every time that you, when you run your regression model on a particular sample data set, you're going to get a particular beta 1 hat value. That beta 1 hat value can be anywhere from the distribution of possible beta 1 hats. So we want that distribution to have a mean or an average value of the true population beta 1. Because that would imply that it is most likely, it is more likely, that our particular beta 1 hat is close to the true beta 1. All right. So that's why being unbiased is so important. Well, what would a biased mean? All right. If the mean of beta 1 hat does not equal the true beta 1, then the estimate is biased. All right, so what does that mean? All right, so now using this red line, imagine that this red line, this red beta 1 is actually the true population beta 1. So now imagine that this red line, this red beta, this is the true population beta 1. But this orange curve, this is the distribution of my beta 1 hat value, and the green line, the green line is then the average of my beta 1 hat distribution. If the red beta 1 is the true beta 1, if the red beta 1 is the true beta 1, you can see that it's unlikely, it's a lot less likely for my beta 1 hat value to be near the true beta 1. See, I'm very likely to get a beta 1 hat value that's right around here, right around the average of the beta 1 hat distribution. That's a good thing if my distribution is unbiased and it's centered around the true beta 1. But if the true beta 1, but if it's not centered at the true beta 1, if the true beta 1 is out here and my distribution is not centered at the true population beta 1, then it is most likely that I will find a beta 1 value that is wrong, that's off, that's far away from the true beta 1. That means that my particular beta 1 hat value is most likely, is almost certainly going to be far away from the true value. So then it's going to, this is what we call bias. It's going to be systematically either smaller or larger than the true population beta, and it's not going to give us a good estimate. We're not going to be able to use it to, we can't reasonably conclude that our beta 1 estimate gives us a representation of the true beta 1 if the beta 1 is biased. All right, so bias is a really big problem. All right, now let me make this just a little bit more clear, okay? So bias is when the expected value of beta 1 hat is not equal to the true population beta 1. All right? It's unbiased is when the expected value of beta 1 hat is equal to the true population beta 1. All right, so this is bias, this is unbiased. Why is bias so bad? Bias means that we cannot trust our estimate to give us an accurate description of the relationship between x and y. Our bias can be upwards or it can be downwards. If our bias if our estimate is biased downwards, then our expected value of beta 1 hat is less than the true population beta 1 hat. That means that our estimate will most likely be smaller than the true effect or the true relationship. Or our estimate could be upward biased. That would be where the expected value of beta 1 hat is greater than the true beta 1. That means that our estimate will most likely be larger than the true effect or the true relationship. If we don't know the direction of the bias, then all we know is that our estimate is almost certainly not a reflection of the true population value. What we know, if our estimate is biased, is that it is not giving us a good representation. And if that bias is large, then it's if the bias is big, if there's a lot of bias and we don't know the direction of the bias, then we effectively just don't have any information about the relationship between x and y. We can't really draw any conclusions from it. Not very meaningful conclusions if it's biased. So bias is a big problem. It is the biggest problem. It's the problem that we are going to be talking about all the time in this class and all the time in my other class. And when you're doing research, you need to really think carefully about bias, because bias is a big problem. If your estimates are biased, then you can't trust them to give you an accurate picture of the relationship between your dependent variable and your independent variable. All right. And this bias is going to be a is going to play a big part also in this question of causality. Throughout the class so far, I have on a number of occasions in the class so far, I've asked you whether or not a particular correlation implies causation. I've asked you if a particular correlation implies causation. I need to correct something. Independence. All right. If a particular correlation implies causation, and so far it doesn't. No correlation implies causation. But if we have an unbiased estimate, then we can conclude causation. Or I could say more precisely, a necessary condition for concluding causation is unbiasedness. All right, so biasness is really important if we want to know a causal relationship between two variables. All right. But unfortunately, it is rare for us to be able to make the conditional mean independence assumption. There's almost always a reason for why our independent variables are correlated with our error term. We're almost always going to have an admitted variable bias problem. Okay? So, and even let me just make this clear. As I titled this section, Omitted Variable Bias. And what I'm saying is that a violation of the conditional mean independence assumption, because there's some excluded variable, there's some omitted variable, causes bias. And so omitted variable bias is the bias that is caused by omitting an important or relevant variable. It's a bias that is caused by omitting an important or relevant variable from the model that is also correlated with the independent variables. All right, so omitted variable bias is the bias that is caused by omitting an important relevant variable, which is also correlated with the independent variables. Omitted variable bias is a violation. That's when we have a violation of the conditional mean independence assumption. All right, an omitted variable bias is one of the biggest problems that we'll face in econometrics. Omitted variable bias is the bias that we experience in our coefficient estimates when we have omitted or excluded an important or relevant variable from the model, which is also correlated with the independent variables or with one independent variable. All right. Okay, so one quick point here, and then we'll keep going on the bias issue. If the conditional mean independence assumption holds, so if this is actually true, we can find what we call the population regression function. The population regression function, what we can say is the expected value of y conditional on x equals the expected value of the expected value of your regression line conditional on x. This simplifies to the expected value of y conditional on x equals our regression, our linear function, plus the expected value of the error term conditional on x. And if our assumption holds, then this will equal 0. And if this equals 0, then we can conclude that the expected value of the dependent variable conditional on the independent variable is equal to this clean linear function. So if the conditional mean independence assumption holds, then the expected value, the average value of the dependent variable, is equal to this, our simple linear model. The expected value, that means that this simple regression model actually accurately describes the average value of the dependent variable conditional on x. All right, what does that mean? All right, so the average value of the dependent variable is purely a function of the independent variable. All right, this is called the population regression function. It's called the population regression function. Let's give you an idea of what this is. So let's see, this is our data, and we fitted a line to it. All right, this is the population regression function. If the conditional mean independence assumption holds, then this is our population regression function. And beta 0 plus beta 1 times the independent variable will equal the average, the expected value of income. All right, so what we can do, we can kind of imagine distributions of the dependent variable for each value of x. For each value of x, there's some distribution of the dependent variable. And each of those distributions has an average. And so what we're saying is that for a given value of the independent variable, we can calculate the average of so each particular value of the independent variable, we can calculate the average of the dependent variable. All right. So for each value of x, for each value of the independent variable, there's some distribution. There's some distribution of the dependent variable. So for each value of x, there's some distribution of the dependent variable. Some distribution of so in this case, income. And the population regression line, when that assumption holds, is equal to the average value of that dependent variable. All right, so each of these are distributions of the dependent variable conditional on x. That means it's a distribution of the dependent variable given a particular value of the independent variable. So this means so the mean of these distributions for each distribution for each value of x is equal to this. All right. All right. Now, with all that said, so we've laid out the implications of this assumption and the consequences of this assumption. We've discussed and kind of demonstrated that, okay, if this assumption doesn't hold, then we're going to have bias, what's called omitted variable bias. And so now what I want to talk about is how do we test for it? How do we know whether or not we have omitted variable bias? So I want to talk about how do we know whether or not our model, the model that we've run, the model that we've specified, has omitted variable bias or not. Okay, so I want to talk about testing for omitted variable bias. And then I want to talk about kind of some solutions. What do we do? Like if we have omitted variable bias, what do we do? What next? Like I said, a bias is a big problem. So how do we solve it? How do we address that problem? Okay. So first, let's do testing for omitted variable bias. All right. The most important means of testing for omitted variable bias is theory or intuition. Now remember from last lecture, I said, and I've repeated again and again, that when we write down a regression model, we want to include all the relevant variables. When we write down a regression model, we want to base that model on theory and intuition first. We think about what is the function that describes the dependent variable. We do that first. That's essential. Okay, and so if the first thing that we rely on is intuition and theory, then that's the same thing that we will rely on to intuit whether or not we have an omitted variable bias. Whether or not there's some variable that is omitted from our model that would be correlated with the independent variable and correlated with the dependent variable. All right, and now in practice, you'll almost always have omitted variable bias, because our data sets will not include all the relevant factors. So we're almost always going to have omitted variable bias of some kind or another. All right. But now, okay, and actually let me go through a couple examples of what this would look like, just to kind of drive this point home. What I'm going to do here is I'm going to pull the two regression model examples that we used in our last lecture, and we're going to talk about whether or not we can infer that there would be omitted variable bias in those models that we ran last time. Now, if you remember, from last lecture, we had specified a model. We said wage is a function of education, experience, ethnicity, and sex. Okay, and so here's our model, and we know that the error term captures all the factors that aren't included in the model. So all other factors. So if you remember, we've got job type, marital status, and we mentioned a bunch of things that might affect wages or might be related to wages that aren't even in the data set. All right, we mentioned one of them is innate ability. So let's think about that one. So we think that ability, intelligence, charisma, things like that. So innate ability is not in the model. So it's accounted for in the error term. Now the question is, does the fact that ability is in the error term, is that going to cause an omitted variable bias? Ability is an omitted variable. Will that cause bias? Is that going to cause bias in one of our estimates? Okay. Well, let's think about that. First, let's pick out one of the independent variables in our model that we're most interested in, or most concerned about. So let's start with education. Let's say education. I'm concerned. I really want to make sure that I have an unbiased estimate of beta 1 because I really want to know the effect or the relationship between education and wage. I want to know how much does wages go up if education goes up. That's really important to me. I'm trying to decide whether or not I want to go back to school. So I want to know how much can I expect my wage to go up if my education goes up. All right, so I really want to know beta 1. So I want to be sure that I'm not going to get a biased estimate of beta 1. All right, so let's think about that. I know that ability is not in my model. It's an omitted variable. Now the question is, will I have omitted variable bias? Well, what are the two conditions for omitted variable bias? One condition for omitted variable. So what are the two things that would need to be true if there was going to be omitted variable bias? Well, one would be that there would need to be correlation between education and ability, right? If education and ability are correlated, that will mean that education is correlated with the error term. And if education is correlated with the error term, then we will violate our conditional mean independence assumption. Okay, so we want to think, is education going to be correlated with ability? All right, but then we have the other condition, and that is that ability would need to be correlated with wage. Okay, I have, I do this a lot. Let's correct this. Wage. All right. So ability would need to be correlated with wage. So if education and ability are correlated, then we violate our conditional mean independence assumption. And if wage is correlated with ability, then we will have omitted variable bias. Now, do we think that we can conclude that? Can we conclude those two things? Well, actually, I think it's somewhat straightforward. Do we think that the level of education will be affected by an individual's ability? I think that's quite reasonable. I think people that are, highly motivated will probably achieve higher levels of education. They'll succeed in school and they'll find opportunities and they'll be motivated to go to college. And so I think that education will be highly correlated with ability. All right, now is ability going to be related to wages? Yeah, sure, I think so. Individuals that are highly motivated are going to work harder in their jobs. They're going to perform better in their jobs, and they'll be more productive, and that productivity will be rewarded with higher wages. And so I think that it's quite reasonable to conclude that the correlation between education and ability is not zero, and the correlation between wage and ability is not zero. Well, that would mean that we have omitted variable bias. Beta 1 will be a biased estimate. Beta 1 hat will be a biased estimate of beta 1. Okay, what about, let's do another example. So let's use the other model that we had in last lecture. All right, so we've GPA as a function of the classroom instructional method, whether it's an online class or it's an in-class lecture format. Okay, and we've got the number of hours that the student spends studying and the student's major. All the other factors are in the error term: intelligence, ability, social network, access to tutors, other various things. Okay, well, let's think about intelligence. Intelligence is not in the model, it's just IQ. So it's accounted for in the error term. Well, let's say I'm really interested. I really want to know how the number of hours spent studying affects GPA. I want to know how many more hours I should spend studying. Right? So I really want an unbiased estimate of beta 3. That's really important to me. I really want to know an unbiased estimate of beta 3. All right, well, I know that intelligence is excluded from the model. The question is that going to cause omitted variable bias? It will cause omitted variable bias if intelligence is correlated with hours spent studying and if intelligence is correlated with GPA. Well, let's think about it. Is intelligence going to be correlated with hours spent studying? I think so. It might be that individuals with higher IQ study less because they need to study less. Or it might be they study more because they know the importance of studying and they're able to digest a lot of information, so they spend more hours studying. Either way, I think there will be a correlation. The same thing with GPA. Students that have a higher IQ will probably have an easier time getting a higher GPA. So therefore, the correlation between hours and intelligence won't be zero, and the correlation between income, the correlation between GPA and intelligence will not be zero, which means the estimate of, in this case we're looking at beta 3, the estimate of beta 3 will be biased. Our beta 3 hat will be a biased estimate of beta 3. All right, so here's two examples of why we might have omitted variable bias. And we can easily think of other variables too, variables that are excluded from the model that would cause omitted variable bias. Okay, so how do we test for omitted variable bias? Well, like I said before, the best way to test for omitted variable bias isn't a formal test, but it's intuition. It's your theory. You got to think about it. Are there variables that are missing? If they're missing, how are they going to be related to the independent variable that you're interested in and the dependent variable? And I think that using kind of this type of intuition that we just illustrated here, you'll realize that there's almost always going to be omitted variable bias. Okay, but we also can use a formal test. OVB, omitted variable bias. So we use a formal test. So this is a statistical method. This is called the Ramsey reset test. So this is some procedure that we will use to kind of formally test for whether or not there are missing variables from the data. And really what this is a test of is it's a test of whether or not we are missing what we call polynomial terms. If you remember from the last lecture, we talked about specifying models where there's some nonlinear relationship between a particular variable and the dependent variable. And I believe in our example, we used the example of experience. And we introduced experience and experience squared into our regression. And so what this test does is this is a formal test to see whether or not our model is excluding polynomial terms, squared terms, etc. So is our model excluding relevant or important squared terms? All right. So this is a test that kind of partially tests for omitted variable bias. What we do is we run our regression model, then we produce predicted dependent variable. We produce the predicted dependent variable, y hat. Then we create power terms, polynomial terms of y hat. So y hat squared, y hat cubed, y hat to the fourth. Then we rerun our original model, but add the new power terms. And we perform a joint f-test on the coefficients for those power terms. And if that f-test is significant, then we reject the null hypothesis that we have omitted we reject the null hypothesis that there is no omitted variable bias. So if we reject that null hypothesis, that means we're missing terms from our model. Our model, we're missing, we have an omitted variable bias. We're missing or missing variables from the model. All right, so that would be our formal test for omitted variable bias. We will demo that both by hand and using a command in Stata. All right, so we have established what is omitted variable bias. We have established the consequences, the dire consequences of omitted variable bias, and we have illustrated how we would test for it. The last question is, how do we solve it? What do we do? What do we do if we have omitted variable bias? Well, the best answer, the most immediate answer would be that we add the relevant omitted variables. We add the variable that's missing to the model. Of course, the problem with that is that oftentimes we don't have all the data. We don't have data on all the relevant omitted variables. So that's not necessarily a good solution. That's not a solution we can always use. The second one, this one we're going to talk about later in this class, and also if you're taking my other course, I will talk about this a lot, and that is we randomly assign the variable of interest. So I'm not gonna talk much about that right now. We'll talk about that later. But suffice it to say for now that if there's some way that we can conclude that our independent variable of interest, the independent variable that we're interested in, like hours from the GPA model or education from the wages model, if there's some way that we can conclude that that is independent of any other variables, then the conditional mean independence assumption will hold and we'll have an unbiased estimate. Okay. Randomization is a way that we can do that. We'll talk about that later. All right. But then the most common thing that we will do when we have omitted variable bias, is that we will admit that we have a problem, and then try to find the direction of the bias. And we'll try to find, is our estimate biased upwards or is it biased downwards? All right, so let's talk about that. So finding the sign of the bias. Is our estimate biased up or is it biased down? All right, so we can use our intuition and sometimes our data to gain insights into the sign of the bias. The sign of the bias is the direction of the bias. The coefficient may be upward bias, and that would mean that it tends to be larger than the true coefficient, or it can be downward bias. It means it tends to be smaller than the true coefficient. Okay. So let's make this clear. All right. So we can use our intuition and sometimes our data to gain insights into the sign of the bias. So let's say this is our true population model. Here's the true population model. The true population model is a function, it has a dependent variable of y, and it's a function of x1 and x2, so two independent variables. But let's say we don't include x2. All right, so the model with the omitted variable is just y as a function of x1. All right, so beta1 hat, our estimate of beta1 hat will be biased if x2 is correlated with y, right? And if x1 and x2 are correlated. All right, so beta1 hat will be biased if these two things are true. Well, let's see if we can sign that bias. Let's see if we can say whether or not beta1 will be biased upwards or downwards. All right, so here we've got this handy table that we can use to reference to think about this bias. All right. So there's two possible options. It's upward bias and downward bias, and we find that out by intuiting or calculating, depending on if we have data for x2. We find that by considering the correlation between x1 and x2, that's up here, and the correlation between x2 and y, which is down here. Okay, so imagine, so there's two different options. Either x1 and x2 are positively correlated. That would mean that as x2 goes up, x1 goes up. Or they're negatively correlated. That means that as x2 goes up, x1 goes down. All right? So positively correlated, negatively correlated. There's also a possibility that y and x2 will be correlated. If there's a positive correlation, there's beta 2 is greater than 0. All right, or negatively correlated, beta 2 is less than 0. All right, so we follow this through. If x1 and x2 are positively correlated, and x2 has a positive correlation with y, then we'll have an upward bias. Okay, if there is a positive correlation between x1 and x2, but x2 is negatively correlated with the dependent variable y, then we'll have a downward bias, and so on. I'm going to demo this in Stata. I'll show you this, and I think it'll make this really clear. All right, so with that, let's jump over to Stata. I'm going to leave this up because I'm going to use it. Let's go down and open up Stata. All right, pull that over to one side. Pull this over to one side. Let's open up our data set. I'm going to use wages 2. All right, so here we go. Let's get started with our demo. All right, I like to take notes. All right, lecture number 5, OLS and omitted variable bias. All right. So let's do a couple different things first. I want to go through the lecture and talk about some different issues, to highlight some different things that we talked about in the lecture. The first thing I want to do is let's start out. All right, let's start out using a simple linear regression model, and then let's illustrate some of the things that we discussed in the lecture. So let's start out with the simplest model. Let's say we're very interested in the relationship between education and wages. All right, so we want to know how education affects wages. Okay, that's what we want to know. So we're going to specify our first simple regression model, regress wage on education. All right, that is our first simple regression model. Okay, so let's run that. So here's our model. Okay. Now, one thing I want to do real quick first is I want to illustrate what we talked about in the lecture when I kind of gave the intuition on what beta 1 hat is. All right, so you'll know from our results here, this is beta 1 hat. This is our estimated beta 1. It's the estimated relationship between education and wage. Okay, this is beta 1 hat. This equals this expression here. So we could calculate this. It also equals the correlation between x and y times the ratio of standard deviations. Well, let's calculate this. I want to drive this point home. I think this is really interesting. So let's do this. Correlation between the dependent and the independent variable, so wage, education, all right? And then we also need to find the standard deviation of wage and the standard deviation of education. All right, so let's run these. All right, here we go. And then let's get out my calculator and let's figure out whether or not that claim is true. All right, so let's start. The correlation between wage and education is 0.4066. All right, and I'm going to multiply that by the standard deviation of wage, 3.709. All right. And then I'm going to divide that by the standard deviation for education, so 2.769. And what do we get? 0.5446. What do we have up here? 0.5446. All right. So that kind of demonstrates it. This coefficient is kind of an adjusted measurement of the correlation between education and wage. All right, and I just proved it. I demonstrated it. Okay. All right. So now let's talk about omitted variable bias. Let's discuss it from a number of different directions. Okay. Now we mentioned, so all right, the next thing we want to do is, well, let's think about it this way. Let's say, so we want to know how education affects wages. We've run a regression. We've gotten an estimate, but now we need to think carefully. Is our beta hat bias? Do we have omitted variable bias. All right, so that's what we're going to think about. Now, step one, answering that question, theory, intuition. Do we think that there is a variable that is missing? Do we think that there is a variable that is missing from the model that is important for explaining wages and that is also correlated with education? Do we think that's the case? Let's think about it. And let's start by just focusing on the variables that are in the data set. Are there any variables that are missing that are relevant to wages and they are correlated with education? I think experience is a big one. I think experience and education will be correlated. I think let's do this. Relevant omitted variables. Okay. I think experience is one. What else? You know, if we remember from last class, I think the female variable is probably one. What about non-white? We didn't think that that was significant last time. Married or job, actually. So I think it's going to be these two. In terms of the data that we have, I think experience and female are going to be important, relevant omitted variables. All right, and we're using our intuition and our theory to kind of intuit that. Now, let's do step two, and that is let's explore this. Let's let the data speak a little bit. Let's see whether or not we really have reason to conclude that these variables are causing omitted variable bias. All right. So what are our conditions? So if there's a correlation between education and experience, so if that does not equal 0, and correlation between wage and experience, all right, does not equal 0, then we will have omitted variable bias. All right, well, let's start looking. Correlation between EDUC and experience. All right, wait. It's easier than that. All right, and then correlation between wage and experience. Okay, so let's take a look. Are education and experience correlated? All right, they have a correlation coefficient of negative 0.2995. All right, so basically 0.3. Now, there's no strict cutoff about what constitutes a big correlation and what constitutes a small one. But a rule of thumb might be that a small correlation is one that's less than 0.1. So I would say this is a pretty strong correlation between education and experience. All right. What about correlation between wage and experience? This is 0.113. It's positive. Okay, so if we look at these two correlations, we would conclude, all right, this is probably going to be omitted variable bias from excluding experience, because experience is correlated with education and it's correlated with wage. It's correlated with the independent variable that we're interested in, and it's correlated with the dependent variable. So looking at these two, we'd say, all right, there's probably going to be omitted variable bias. So we can take note of that. Probably omitted variable bias from excluding experience. Now let's ask ourselves, what is the sign? What's the sign of that bias? All right. To answer that, let's pull up our table that we have on the second to last slide, and let's take a look at it. So the correlation between x1 and x2, in our case, that would be the correlation between education and experience. All right, is it positive or negative? All right, it's negative. That means we're over here. The correlation between education and experience is negative. All right. Now, what about beta 2? What about the coefficient on experience? Well, we can kind of infer the coefficient on experience by looking at the correlation between wage and experience. All right, so the correlation between wage and experience is 0.11. It's positive. All right, so that means beta 2 would be positive. All right, so let's follow that over. We've got a negative correlation between education and experience, and a positive correlation between wage and experience. So come over, we'd say it's downward bias. It's going to be a downward bias. So what is the sign? So we can imagine that, we can even reinforce this with our intuition. We can say that the more education you have, the less experience you have. Well, that makes a lot of sense, because if you spent your time in school, you haven't spent your time working. So, okay, education and experience are negatively correlated. Wage and experience are positively correlated. That is very intuitive, right? You have more experience, you're probably going to have higher wages. All right, and so then this would imply that we will have a downward bias. All right, so we'll have a downward bias. What does that mean? That implies that basically our beta on education is smaller than it should be if we exclude experience. So smaller than it should be if we exclude experience. So we would predict that if we add experience to the model, that the beta on education will increase, because there's a downward bias being caused by the exclusion. There's a downward bias being caused by the exclusion, the omission of experience. Let's look at that. All right, we've used our intuition and we've used the data to kind of get a really clean understanding that yes, there probably is bias, and the bias is a downward bias. Well, let's test it. Let's look at it. All right. First, let's rerun our model from before, wage and education. This gives us our baseline. Okay. And what we're saying is that 0.54 is downward bias. This is smaller than it should be. This is an inaccurate picture of the relationship between education and wages, and it is smaller than the true relationship between education and wages. Well, we think that we have some omitted variable bias by excluding experience, so now let's add experience and see what happens. And so if we're correct, then the coefficient on education will be higher once we've added experience. What do we find? The coefficient on education when we've excluded experience is 0.54, and now the coefficient when we've added experience is 0.65. We were right. We were totally right. There was a downward bias, and now we get a larger coefficient. All right, so we've been very clear and very point by point going through and kind of thinking, is there correlation? Is there a motive variable bias? We decided that there was. We decided what the sign was. We predicted it, and then we ran the regression, and look, we were right. All right, let's do it again. Let's do another example. All right, let's think about the female variable. All right, I'm just going to copy and paste this. All right, so if there's correlation between education and female, correlation between wage and female. So if there's correlation between these two, then we'll have omitted variable bias. So let's do the correlation coefficients. Education, female, correlation between wage and female. Okay, now let's use our intuition first. Do we think there will be a correlation between education and being female? This one's a lot less obvious from before. And I think that the time period for this data set might be relevant. The time period is going to matter here. The data set that we're using is from 30, 40 years ago. Now, 30, 40 years ago, we might expect that men would typically have more years of education because 30, 40 years ago in the United States, it was probably more common for men to go to college than women. Now, if this data was from the present day, we actually might expect it to be the opposite, that women have more education than men, or to be roughly the same. But taking note of the fact that this data is from the United States from 40 years ago, then we might expect that that men have higher levels of education than women. All right. Just the cultural reasons. All right. Now, do we think that there will be correlation between wage and female? Again, this is a tricky question. There's a lot of research on this. But the research is very clear that, at least on average, not controlling for anything, that that men typically make higher wages than women. So we think that there probably will be a correlation here. It's our intuition, based on our intuition. So if this is true, we'll have a admitted variable bias. Now let's look. Let's look at our data and see what we find. Let's run our correlations. So first, is there a correlation between education and female? Okay, there's a small negative correlation. This is pretty small. It's less than 0.1, so it's pretty small. Men have a little bit more education than women, but it's very, very slight. It might not be significant. All right. What about wages in female? Okay, this one's larger. So in this data set, there is a strong negative correlation between wages and being female. That would mean that men in this data set have higher wages than women. All right, let's pull up our table. Actually, make note of this. Based on this, do we think there's going to be an admitted variable bias? This is a pretty large correlation. This one's pretty small. So when we look at this, we might say, all right, there might be a small amount of admitted variable bias. But because this is small, then it might not be too bad. So maybe a small amount of omitted variable bias from excluding the female variable. All right, but now what is the sign? All right, let's think about it first. Let's intuit it. Actually, we already did. So education and female are negatively correlated. Wage and female are negatively correlated. All right. What does this imply? This would imply, let's go to our table. All right. So the correlation between education and female is negative. The correlation between wage and female is negative. So this would imply an upward bias. Okay. So this would imply upward bias. All right. That means that our coefficient on education is larger than it should be if we exclude or omit female. So we would predict that if we add female to the model, that the beta on education will decrease. All right. So now we've done it. We've been methodical. We've planned it out. We think that there's bias, a small amount of bias, and we think we have the sign. So let's do our baseline case, wage education. And then, actually, as our baseline case, we're going to use the model with experience too. And then let's take our model, EDUC, experience, and let's add female to it. All right. So here's kind of like our baseline. We're comparing this. All right. So education, the coefficient is 0.65. So now we would expect, based on our discussion, we'd expect that there will be omitted variable bias, and that will be an upward bias. So that means when I run this regression, we would expect that the coefficient on education will go down. All right, we're removing some of that upward bias, so let's hit it. Boom. What do we see? And it's beautiful. 0.61 basically. So was there omitted variable bias? Yes, a small amount, smaller than with experience. And it was an upward bias. So once we add female, it goes down. All right. So that illustration kind of demonstrates to us that we had omitted variable bias. Now, one thing that I want to point out here that's going to be really important that I want you to think about when you're doing analysis, okay? This is going to be very important. One thing that you'll notice here is that, we really thought this out, and we really thought about whether or not we had omitted variable bias and what variables were missing and what would happen if we added them. But one thing that you'll notice is that when we have omitted variable bias, that when we add additional variables, the coefficient changes. All right? So in both cases, the coefficient changed. So when we added experience, the coefficient on education changed from 0.54 to 0.65. When we added female, the coefficient changed from 0.65 to 0.61. All right? Now that means that in the future, when you're running analyses, if you run one regression and then you add a variable and run the regression again, if your coefficients change a lot after adding additional variables, that means that you must have had omitted variable bias. Okay, so that becomes kind of an informal kind of test or confirmation that there was omitted variable bias. If your coefficients are changing when you add additional new variables to the model. And so you want to pay attention to that. If you're doing an analysis and you're adding variables and the coefficients are changing every time you add variables, that means that there's some omitted variable bias problems, okay? And you have to be very careful that you specify the correct model and you include all of the relevant variables that you're able to include. Okay, so you just want to watch out for this. You want to watch out for how these coefficients change when you add new variables. Okay, so I'm just going to make a note of that. Note that when you have omitted variable bias, the addition of relevant variables are likely to change your coefficient estimates. So if you see your estimates changing as you add variables, then you want to pay careful attention to the omitted variable bias problem. Okay. All right. Excellent. Now, so a couple more considerations before we close. The next one is, one thing that you'll notice from this exercise here is that, in our original model, so in our simple model, we definitely had omitted variable bias. Excluding experience caused omitted variable bias. We notice here that we still had omitted variable bias, that if we included female, that we had omitted variable bias by excluding the female variable. Now the question is, are we done? Have we included all the relevant variables? Well, we could add, we could add another variable. To get an idea, let's add non-white. All right. Now we thought from the last lecture that non-white's not really relevant. Let's run it. We know that the r squared goes down when we add it. We know that it's not significant, so we don't really think it's relevant. Does it change our coefficient very much? Almost not at all. Okay, so we don't have omitted variable bias from admitting non-white. All right, so we don't need that. But now the question is, are there variables that aren't included in our data set? Like just because, so we definitely had omitted variable bias before. We definitely had omitted variable bias when we just did the regression of wage on education. And we definitely had omitted variable bias when we excluded female. But just because we've added experience in female doesn't mean that we've gotten rid of the omitted variable bias. There could be other variables that aren't even in our data set. Like we haven't solved the problem just by including experience in female. We have to think, are there other variables? Are there other factors that would affect both wages and education that we don't even have in our data set? All right, so we might have omitted variable bias because we exclude variables that aren't that are not even in our data set. That means, that we can't solve the problem by including them because we don't have data, because we don't have the data. All right. Can we reasonably say that there is such missing variables? Some ideas of omitted variables. Well, one of our go-tos so far has been ability. Another one could be some measurement of social network. That's huge in terms of getting jobs and making good wages. It could be other things, but just those for now. Do we think that there's going to be omitted variable bias from, let's say, excluding ability? All right, let's put this here. Is education going to be correlated with ability? Well, we talked about that in lecture, and I think the answer is yes. Are wages going to be correlated with ability? And again, I think the answer is going to be yes. So probably we will have omitted variable bias from omitting ability. But we cannot add it to the model. So we have a problem. We can sign the problem. So let's sign the problem. What's it going to be? So is the correlation between education and ability going to be positive or negative? I would say that's probably going to be positive. All right. Is the correlation between wages and ability going to be positive? I think it's probably going to be positive. So we'll probably have upward bias. Yeah. So let's sign the problem. Probably upward bias. So that means that the coefficient 0.61 is probably larger than it should be because we're excluding ability. But there might be other omitted variables. So you can see that omitted variable bias is a big problem, and it's hard to solve. I think we've done the best job that we can in this particular example to control for it, because we've included education, experience, and female. But now at this point, what we might do is we might do a formal test. So let's do a formal test for omitted variable bias. All right. And we're going to use this model. This is the best model that we have using our data so far. Let's test whether or not this model has omitted variable bias. So we're going to do the Ramsey reset test. All right. The Ramsey reset test. All right. So let's do this step by step. We're going to run the regression model. All right. There we go. We have it there. Then we're going to produce predicted dependent variables. All right. Predicted dependent variables. Let's do that. Predict. That's all you have to do. Predict. What is it? Y hat. All right. That's going to be the predicted dependent variable. Then we need to create power terms. So let's do generate y hat 2 equals y hat squared. Gen y hat 3 equals y hat to the third. Gen y hat 4 equals y hat to the fourth. All right. Then we're going to rerun the model. wage, education, experience, female, and we're going to include all of these terms. All right, and then finally we will do a joint f-test, so we test the hypothesis that these terms are all equal to 0. If they're not equal to 0, so the null hypothesis for this test will be that all of these, the coefficients for all of these terms will be 0, which is another way of saying that we do not have omitted variable bias with respect to polynomial terms like squared terms. If we reject the null, that would mean that we do have omitted variable bias. Okay, or that we would conclude that we have omitted variable bias. All right, so let's do this. First, let's run the regression. All right, let's run the regression, and then we're going to predict y-hats. We're not going to see anything here. All right, then we're going to generate these polynomial terms. Generated them. Excellent. We can look in our data set, find them. All right, y-hat squared, y-hat cubed, y-hat to the 4th. All right. Now let's run a regression with those terms in it. So y-hat 2, y-hat 3, y-hat 4. Now we're going to test the null hypothesis that these are all equal to 0. All right. So it is highly significant. That means we reject the null hypothesis that all of them are equal to 0. And we would conclude that we have evidence that there's omitted variable bias. All right. So that's the Ramsey reset test by hand. Let's do it just using a stata command. All right, we'll just do estat ov test. So omitted variable test. All right, let's run this. Same thing. Ramsey reset test using powers of the fitted values of wage. Model has no omitted variables. That's the null hypothesis, is that the model has no omitted variables. The p-value is highly significant, and so we reject the null hypothesis, and we believe that there's evidence that there is omitted variable bias in the model. Okay, so even though we've included experience and female, we still have, from this test and from our intuition, so using the formal test and our intuition, we would conclude that we still have omitted variable bias. All right, we will try to solve omitted variable bias in a more complete way later in the course. But with that, I thank you very much for your time. I look forward to seeing you in class. Be sure to study this lecture hard and to come to class prepared. And with that, I hope you have a great day, and we will see you later.